Last time we've ended with a look at a somewhat weird construct, maybe the first time you see it. And let me get a rough rundown of it again. So we had a class. Oh, let's call this one just C. No. Let's be somewhat more creative. Some ref. Of course, it's a reference type, it's a class. And internally, what we stored was just some ref. It's called ref. And we're gonna leave out the constructor, because as we learned last time, we don't actually need to specify a constructor in here. If we leave it completely empty, the compiler will add the default constructor, which doesn't receive any arguments, which doesn't do anything internally, which still allows us to create a new ref. So we can still do some ref in here. Let's just go for A. Just a new some ref. Can still do that. This is still valid. This constructor technically exists, even though we didn't write it ourselves. And it will simply cause the system to reserve space on the heap. This is a reference type, a class, so the neo keyword will actually trigger the system to find some empty space on the heap and reserve that space for us. And the constructor is just to make sure that we did call a constructor. Even if it's not doing anything, we do have to call it. It's just a part of the standard procedure. And that leaves us with a value for ref, which is initialized as just zeros in memory, because that's what the preserving in the heap does. As we discussed last time, that means that a.ref is now null. I can't use this to get another ref, for example, because this is just zeros. This points to an address 0 in our memory, which is not a valid memory address for us. It's just used as a marker to say we don't actually have a value in here. So we should first start by adding another value, which we can do just another assignment and another constructor call. Some ref. And now we can do a.ref.ref, which itself now would be null because we just created it with the default constructor, leaving the variable ref just as zeros, meaning null. But we can do this again, assign some other value. And we can continue this as much as we like, as long as we have free space in our memory. And considering that all we store is just a memory address, and our memory usually is pretty large, this will take a while. What I didn't show you last time is what happens. Let's just clear this up. Should have cleared this up a bit differently. Better. Let's do the same, but this time we're doing it for a struct, and this is some val, because it's a value type this time. And this will store some val. The same structure as we did down here, with a struct which stores itself. But what would this look like? How would this work? I can close the bracket. Okay. Focus. Good enough. Once you start typing just on the computer, you slowly unlearn writing by hand. It's a curse. Anyway, what would this look like? Let's keep in mind the system as it exists. We have the type in value, our good old table, which I will slowly phase out soon. Or maybe we'll start today. And we have the heap. So if we had some ref like before, I'm just gonna call it S now, S blah blah blah, A, it would have an address to somewhere on the heap where we store one sumref. So we have another table down here which has another some ref called ref, and this might be another address which might point to another object somewhere on the heap, or it might point to itself. It can contain its own address, that's fine. Or if we just create it with a standard constructor and do nothing else, this will just be null. So we know exactly, in all cases, what this thing, except for this value, looks like. No matter how we use it, we know exactly what the variable sumref A would look like. We know what the stack would look like. We know what the heap would look like. We don't know the details for the specific value down here or up here, but we know the general layout. And most importantly, we know how big it will be. This will contain exactly one address. We know how big addresses are. That depends on the architecture, but the computer will know itself when it starts the program how large an address would be. How many bits are needed to store one address in memory. So we know this is how much space we need on the stack. And in the same way, down here we store only one address. We know how big this needs to be. Because we store only the address, it needs to have enough space for one address. With a struct, with a value type, I create a sumVal. sumVal B. Well, this doesn't contain an address. This contains the full value we store. So this has internally another table. The heap doesn't come into play at all. And what do we store? Well, we store some value, val, and well, some val is a value type, so we store another table. For one sumVal, which has sumVal, val, which stores another table. And you can see where this is going, right? This is an infinite sequence of values inside values inside values. We need enough space on the stack to store one sum value. Well, how much space do we need for one sum value? We need enough space to store one sum value. Alright, so how much space do we need for one sumVal? Well, it contains one sumVal, so we need enough space to store sumVal. This is an infinite loop. We have infinitely many tables stacked in one another in here. That's not possible. I mean, maybe it makes sense in a universe where we have infinite amounts of memory. It could be interesting. Computers that inherently work with the concept of infinity, not just use mathematical constructs to describe it. But in the current world we live in, this is not possible. And therefore, this is actually not allowed. You can't have a struct that internally stores itself. You could have another struct, that would be fine. So we can have struct some other val, right? That's fine. This struct is a different struct, a different value we can determine on itself, and that's added into this struct. There's no conflict here, there's no infinite looping of different types. What would be a problem if this now stores internally some val? So some val would store some other val, but some other val would store some val, and that would give us this infinite loop again. That's not possible here. The only reason we can do it with classes, with reference type, is because we don't actually store the real value. We only store a memory address. And very importantly, this memory address doesn't need to be real. We can use null as a value to determine that there is nothing to store. We have the concept of nothing. But with a struct, we always have to have something. We have to make this sequence infinitely long. With a reference type, we can just cut it off. We can just say up here, nope, there's nothing in here. It's just null. And we don't need to look into the value down here because there is none. So the weird construct I showed you, where we have a value that stores itself, which stores another value of its own type, which stores another value of its own type, that works with reference types and is actually used for some really cool stuff, which we will look in the future at. But it's not possible with values or value types. Since we're talking about structs and classes that store reference to other structs and classes, what happens if we mix the two? Let's clean this up a bit. I can clean up. Oh, I can, okay, but I'm messing this up. So let's say this is not some ref, this is some val. And this is not some val, because that would not be possible, but some ref. This would be perfectly possible. This is legal code. You can do that. So we'll create some val. Things are pretty simple. We have some val A, which is a new some val, which means we have here a some val A, which has internally a table, of course, because it's a struct, it's a value type. The full value is stored in here, and it stores one some ref, which by default, because we didn't provide any values, is just null. No problem. We could use a.ref and assign a new some ref. What happens now? Well, we have the new keyword, so we reserve space somewhere on the heap. Let's do it somewhere else this time. For with enough space for one sumref. Right, and this has some address. And because we assign that in here to the ref in A, we'll just adjust the value in here. And this will now be the address for our value stored on the heap, for our object on the heap. And this new sumref will also start with, well, everything set to 0. What does it look like when I set everything to 0 for a value type? For reference type, it just means, well, this is pointing to memory address 0, which the computer understands as it doesn't point to anything. There is no meaning to this. It's an empty variable. But this is a value type. SumVal is a struct. We have to have something in here. We can't just leave that as doesn't exist. Well, not really a problem though. When we set everything to 0, it means we create a table still for all the variables in here. So we have some ref, but we just start with all the values set to 0. Meaning sumref is a reference type, so this is still null. As you can see, we can quite easily mix structs and classes without any issues. If we have a struct that stores internally a reference, well, then we just have a struct which internally has a reference to somewhere on the heap. And if we store a struct within a reference, value type and reference type, well then whatever we have on the heap will just be the struct. Which might be the biggest change so far in terms of structs and classes. So far, structs always lived in the stack. Whenever we created a new struct, it was always in here on the stack. It was always the value, always a little table in the big table. But because this time this struct is part of a reference type, this class sumref, we don't add this val on here on the stack. It lives down here on the heap, within the boundaries of sumref. So both value types and reference types can exist on the heap. Value types can exist entirely on the stack, whereas reference types can never exist on the stack. So reference types are always limited to the heap itself. The reference, the address to that part on the heap can be put on the stack, but the actual data will always be on the heap. Value types can be put on the stack directly, or they can be stored somewhere on the heap. Depends on context. Maybe one last thing regarding setting the memory to 0. Let's clean this up. Let's clean this really up. Please, just good enough. Setting the memory in the computer completely to zeros has different meanings for different data types. We've discussed that. Setting an int all to zeros, well, that's just 0. Taking a float to 0 is also just a number set to 0. 0.0. For Boolean, it just means false. And for a reference type, that just means it's null. It's not pointing anywhere. And as you've now seen, for value types, well, it's just the exact value type where all the contained variables inside that value type start at all zeros. So no different than the reference type with the default constructor. Thing is, sometimes you have, or you will run into situations where you might not be sure what the exact value will be, but you want to make use of this setting everything to 0. You want to ensure that a variable is starting off with a neutral value, with something recognizable as this is not a specific value, it's something neutral, something, a common starting point. Why you might do this depends very much on the context in which you're working with. We will eventually get to some situations where it is necessary. But otherwise it might just be you're too lazy to think about what data type you have and what the neutral value would be that the compiler decides on, if you can't define your own. And I'm talking a bit too much about this. It's very simple. Instead of writing out these individual neutral values for each type, where everything is just set to zeros, we can use a keyword to tell the compiler to automatically use whatever it defines as the neutral value. And the keyword is default. So it's not a neutral value, it's the default value. The value the compiler, the computer would use when it sees everything set to 0 in memory. All the bits are 0, that's default. So we can set that to default, and we can set this to default. We can set this as well to default. And this is default. And this is default. Well, kinda. In any case, you can always use the keyword default to assign a memory value with all zeros. And depending on the type, this has different meanings. So you don't have to think about what type you have. If you want all memory bits set to 0, just use default. That's the equivalent of what happens if you create a new sumVal or a new sumRef internally. Right. Enough of that. Let's deal with something more interesting. Let's change this to a class, and we just call it value. Not because it's a value type, but because internally we store a value. An integer value. And we can create a new value, so value A is a new, let's do this somewhat correct, it's a new value. It will start with a default value for integer that is 0, so our A will internally store a 0. Actually, let's get rid of this because I think it's just getting in the way, and I don't think you need it right now. Just distracting. And it takes up space. And let's create another value. B, which is also a new value. Whatever. And then let's say a.val is equal to 5 and b.val is equal to 6. Right? Pretty simple program. We have two values. One stores a 5 internally, the other stores a 6 internally. Now, let's say I want to compare these two. I want to compare A and B. Say I have an if, and I want to do something if the two of them are equal. So we've learned about comparisons, so A equals B, like that. Right? A equals B. It will compare the two, and if they're equal, then this evaluates to true, right? Kind of. You see, I can do this actually. I can directly compare two values, two reference types, at least if they're the same type. I can just compare them like this. That is fine. It's just the thing we're comparing is not the thing we care about. Actually, we kind of do need the table now. Just quickly on the side here. So we have two values, A, B, and this one has one address, 1, 2, 3, and this one has 999. Let's put it like that. When we compare A and B, the comparison, what it compares is the immediate value of A and B in our table. That means it's comparing 123 to 999. So 123 is not 999, so this would not be equal. Which is fine in this case, because the values internally are also not equal, so it's matching what we want. Now it's a problem. A and B internally store a 5, both of them. They look identical in memory, but that is on the heap. A and B look identical on the heap. The two values stored in address 123 and 999, they have the exact same sequence of bits. They both store a 5. But when we compare these two, we don't compare the values at the address, we compare the address directly. If I do A equals A, well, yes, this will evaluate to true, because 123 is 123. We compare the address, and of course, the address is equal to itself. I could have a value C equals A, and all I'm doing here is copy the address, right? So A and C are actually the same address, even though they are two distinct variables on the stack. So I can compare A and C, and this also would be true, because they both have the same address. The value in here on the table, on the stack, is the same. But we want a comparison between the actual values on the heap. How do we do that? Well, the unfortunate answer is there's no easy way to do that. The reason being, The computer doesn't know how we define being the same. The computer doesn't know how we would compare two values. Even though it might seem obvious right now, it only stores an integer value, so compare the integer values. What if this becomes a bit more complex? What if you have not just one single integer, but dozens of different values, intermixed with other custom types you've defined? Maybe some of the information is just additional information you store in here, but that's not relevant for the overall type. So for example, bool updated more than once. Kind of a stupid variable, but situations like this could happen, where the actual value I care about is just in val. But I do store other variables in here that give me some more context for how I used it and some metadata that is not relevant to the actual information I want to store in here. If I compare two values, I might not care about this updated more than once. Or maybe I do care, but that might change depending on the context. The way we would solve it right now is, well, we go specifically for a.val equals b.val. Right? It's the most direct way to handle this. In our if, we make the exact comparison we would want in our situation, whatever the situation is. Maybe we only care about the value. Maybe we do care about this boolean as well, in which case we could extend this condition to a.val equals b.val, sure, and a updated more than once equals b dot updated more than once. It's a lot more to write, but we have full control over it now. Now imagine you have to do that a couple dozen times in your code. Sometimes with the and, sometimes without. Doable, but certainly not the most elegant way to handle this. Well, luckily for us, we can just write a method in here that will do that for us, right? We can just create a method which returns a boolean, and it's called is equal to. Let's put it like this. Is equal to, and it will receive another value. It's a parameter. Let's call it other. Well, maybe that, yeah, good enough. And it will return the exact same condition we wrote earlier. Return val. Since we're now inside our class, since it's a method contained within the type itself, we have direct access to the variable and don't need to reference any other, at least for ourselves. And we can return val equals, and now we have to reference this other value, which is a reference we get from the outside. Again, we have a method inside our class, so we work in the context of a very specific value on the heap somewhere. So if there's a heap with the val, right, that's an int val, and that's a boolean update, blah, 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 blah. This method operates in this context using this table. And other is just a reference we passed on from somewhere outside. So val references our own table, this val directly, while other is this address here, another object on the heap, where you can get another val from. It's the same as saying a.val here would be just val maybe down here, and b.val is the same as other.val. And so what I can do now is I call that method a.is equal to b. Inside the brackets for our condition, for our if, we make a method call, which is perfectly legal. I mean, it's just normal code, which will return a boolean. So once this method returns, we will have a boolean value in here, a true or false, which is used as the condition for executing this if, or skipping it. And all the logic necessary to make the comparison is contained in this method. We can expand this to make it larger. Just continuing on the next line here, and update blah 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 equals other dot update blah blah blah. We could continue like this. We could extend this to include by default both variables. We could change that in our type. We define ourselves in our type how this type should be compared with others. And our original code here is just going to use that. If we ever add another value, maybe there's a second value, just going to be val2. I'm going to be creative today. We're just going to extend this. Val2 equals other dot 2. And we don't need to change anything up here. We just changed this method after changing the type itself. So the entire logic for comparisons is handled in our class. And we could do the same if this was a struct, of course. Be it struct or class, in both cases we can create a custom method to make a comparison, which has its own context, of course. Though in that case it's not on the heap somewhere, but the context is on the stack still, doesn't really matter. Functionally, it works the same. We have val, our own value, and we have other, which is the other value we compare to. For a struct, we get the full value, we get a full table with values in here. And the way we have it here with a class, well, we just get the address on the heap where we look up the data. The code will still look the same and will work the same. That's all pretty useful. But there's one issue we have to discuss specifically when using classes. Let's skip this part. And let's skip this part up here as well. And move things up a bit, because I don't want to write that again. What if both of these are null? Because we haven't defined a proper value for that yet, or maybe because we are working with references we get from somewhere else, which might not have been initialized internally, because it's just using default values. Something like what we had before. Let's simplify this to just one val. Well, that option means we have to do a few things. One thing we can do immediately, we change, actually I should have just moved everything up. That was my mistake. Yeah, that will work. One thing we can do, we check other. You see, as I showed you before, when we make a comparison, an equals equals, for reference types, what we actually compare is not the data, but the address itself that is stored directly in the variable. So if I compare other to anything, what I'm comparing is not the data that other might reference. It is other itself, the memory address stored in here. I'm comparing that to something. And what I can compare it to is null. Should probably write this out a bit. This is U and this is an L. Can't write. I can use the keyword null, just as I can compare val to 0. So can I compare other to null? Null is also just a value. It's not simply a keyword, it's a value. I can use it for operations. And I can, where did I add a semicolon here? I can do this kind of comparison to see if other is actually just null, if it's actually pointing to nothing. And if that is the case, then, well, we are right now in one value, and we compare it to another value. And this other value we try to compare it to is null. So in that case, we just return false. No need to compare any further. If we have a definitive value, we are actually inside an object on the heap. We are not null. Keep in mind, we are calling this method on an existing object on the heap. That's the only way we can call this method. We must be in one context that actually exists. We are definitely not null. This other thing we get from the outside might not exist. That might be null. And that's what we check here by comparing it directly to null. And in that case, well, we are not equal. We're actually something that exists. Other is something that doesn't exist. It's null, it's nothing. So we're not equal, we can return false. And if that isn't the case, well, we skip this return statement, the code continues, and we do this one down here, where we actually make a comparison between us, our real values, and the other values. That's only step one. That would work if A had an actual value. Then we could do A dot is equal to B, where B might be null. We could actually do, I'm saying a lot of actually today. We could just insert null in here. That's fine. We can use it as a value, we can pass it on, and the code would still evaluate that correctly. But we're not just setting B to null. It's a bit trickier than that. A is also null. And what does that mean? If both A and B are null, then there is nothing on the heap we can compare. There is also nothing we can call a method on. A points to nothing. There is nothing we can call this is equal to on. There's no one there to execute this method for us. There's no context in which we can execute the method. So this is actually not allowed. The computer would complain at this point. Now, when the computer complains is a different story. In older systems, older versions of C#, it will definitely complain when you run the computer code. It would do everything just as you said, it would compile the code, it would run it, and then it would start complaining here. And it will complain in a very specific way that we will get to at some point. It's a bit higher level now. We'll get to it. In newer versions of C#, you can actually make it so that the compiler already complains before the program code is compiled. So while you write it, it will already complain and tell you that this is not possible. But you need to set some things up for that, and also another topic we'll cover in the future, in the near future. So what do we do now? Assuming the compiler doesn't warn us of it beforehand, and we don't want our program to run into any issues during runtime, how do we deal with this situation? I mean, straightforward. We do the same we did down here. If A is not equal to null, so if A is not just all zeros, if it has actually value, the opposite of equals equals, and A dot is equal, that's one way to do it. But we probably want the logic to be if both are null, they're still considered equal, right? Both are null, both are literally the same. All zeros. These are identical in value. So we could create a whole set of conditions now. Can say if A is null and B is null, they're both equal, and we add some brackets now just for clarity. They don't technically need to be there. Or if A is not null and A dot is equal blah 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 blah. It's a bit longer, but we could do that. Either they are both null, or A is not null, in which it all comes down to this equals to method, which will take care of other, in this case B, being null or not. So this is a full condition we could write out to make sure to execute code if A and B are the same, they're equal, regardless of being null or not is a possibility. It will always work the same, the compiler won't have any issues, the computer won't have any issues, and the outcome will be predefined by us and consistent. Great. Except we have another case where we write out a complicated condition up here in our if, even though we already started putting it into a method. How do you get around that? Alright, so what's the issue? We want to have a method somewhere else that we can call repeatedly whenever we need to compare two values. So far we've put that into the value class itself, which meant that to make a comparison we need at least one functioning value. Which shouldn't be a problem in most cases, but sometimes we might not have a functioning value. And we still want that to be one of the cases in which we call the method. There is, of course, the option to create a different class. We could have something like a class compare, which doesn't have any values on its own and just does a bool not is equal, are equal, which receives two values, A and value B. And this method will take care of everything. And we just have to create a pair C equals new pair, like that. We'd only need the default constructor because there's nothing in here to use. And then we can do C dot R equal A, comma B. And the logic in here will take care of all the checks for are they null? If so, are they both null? If not, what do we do instead? And we could actually, I said actually again, what is it today? We could use the entire logic we have in here and put that fully in this method, in which case value doesn't have its own method anymore. Could do that. With this, we can reuse the same method multiple times, as many times as we want, and we don't have to worry about A and or B being null. It still will work out, there won't be any issues when we run the program, and we will get consistent results. Only now we constantly have to create a special variable C, or some other name, which stores a compare. An object that doesn't store any data, that only exists to add functionality. That's kind of annoying. I mean, there are worse things, but it's definitely not ideal. And so in C# we have actually, I was about to say it, we have an alternative. See, so far when we created custom type, it meant we just created the definition for how this data type works. When we add it as a struct directly in the table on the stack, or if we create it somewhere on the heap as a single object, we just provided the definition for how it looks and how it will work. And that is applied as a template to every new instance of that custom type, on the stack, on the heap, wherever. The definition for custom types has, however, a special keyword we can apply that lets us make definitions not as a template for specific instances of that type, but for the type in general. And maybe it makes more sense if I just demonstrate. Let's remove this for now, just to get some space. And let's also this. Yeah, okay, good enough. And we can do that with a specific keyword, which is it has some relation to another keyword you already learned about. This other keyword is const, which allowed us to define a constant value. We can create a variable, we can mark it with the constant keyword, const, and that will allow us, const int I equals 42, for example. This will mean we have now a variable I defined that will always be 42. No matter what we do, we can't change I anymore. The compiler won't allow it. And the way it works internally is it basically drops the I internally as a variable, because it's not variable, it's a constant value, and effectively it will just replace every occurrence of I with the full value 42. And a similar concept, not the same, a similar one exists for custom types. And in this case, the keyword is static. Static is used to define something in a custom type that is not specific to one instance of the type, but a common thing across all iterations of that type. I'll just write this out first and then demonstrate. That might make it easier. We're gonna do the equals method again. Static, bool. The rest is the same as before. We create a method. We just start with the static keyword. But the rest is just a normal method. Bool r equal. We're doing the thing we did with the compare before. And r equal will receive two values. Value a and value b. Just like the method from our custom compare class earlier. Except for the static keyword in front, this is just a normal method. What's special is, since we are not tied to a specific instance, we don't have access to val. This doesn't work. We don't have access to val. Usually we would be, if it's an object somewhere on the heap, we would work in this context. This is a given. This table exists. It's all these variables we defined in our custom type, and that's what this method would work with, alongside the parameters. But because we made it static, we said it's not tied to one value. It's more general, it's a global thing. It's not really part of this type directly. It is somewhere outside of the stack and the heap. I think I mentioned this when we introduced the whole concept, but we had the stack and the heap, and I said those are the two parts of memory you work with. But there's at least one another part in memory that is used for your programs, but that you don't interact with directly. And you can imagine it like with a static, we tell the compiler, please use this code outside of these two parts of our code. Like we are somewhere outside of these two, outside of stack and heap, and that's the context in which we execute this. Which just means we don't have access to anything on our stack or on heap directly. The only thing we get are the things we provide in those parameters. So val doesn't exist because this is static. If this was not static, we would have access to val because then we're in this specific context, or maybe this context, or this one. Or if this was a struct, we might be in the context of up here, because static also works inside a struct. No difference there. What we can do now is if a equals null or b equal, not or. If a equals null and b equals null, then we just return true, because we consider that to be equal. And in this case, a and b both are null. Honestly, why does my null look like 3 identical letters? I should practice handwriting, I guess. But we won't need it after today, hopefully. Anyway, yeah, we check that, and if both are null, we are true. And then we can make another check if a is null. Let's just not be smart about this and just make it simple. Actually, no, let's be smart about it. A equals null, XOR B equals null. A bit smart at least. So reminder XOR, this little hat symbol, just a little triangle at the top. This just means the left side or the right side, but never both, and never none. So true and false, or false and true, that would be both evaluated to true, but if left and right are true, or if left and right are false, then this whole thing would evaluate to false. And what we do here is we just make sure that if both are null, then they're equal, return true. If only one of them is null, exactly one of them, then return false. And if neither of these is triggered, that means they can't be both null, and there's a combination of one of them being null and the other not. So the only option left is both are not null. And then we can do the whole return a.val equals b.val, and done. Because down here we know already that a and b are definitely not null. Okay, just very simple way to make the comparison. There are shorter ways to write this out, by the way, especially with newer C# language features, but we're not concerning ourselves with that right now. So we created a method that's not tied to one specific variable anymore, to one specific instance of value. So how do we call that? Before I would use a dot is equal, or b dot is equal, or maybe c dot are equal. What do we do now? That's the wonderful thing about statics. This method isn't tied to one specific instance, but it is tied to something. It is still tied to this type itself. We write that inside this class value. It is tied to our custom type value. It might not be tied to a specific instance, to a specific object of that type, but to the type in general. And so we just write the class name and then make a dot. Which will look weird the very first time you see it. Because it's like, what do you mean I can just use the class name as a variable? That's nonsense. But it works, because are equal is static. Similar to const, it's not an actual const is not an actual variable anymore that we treat like normal variables. We just use the syntax for creating variables to help us define something. In the same way, by marking something as static, it's not a regular method we apply on a specific instance of something. We just use the general outline for methods as a convenient way to define this static method. We have to define it somewhere, and of course, if it's tied to a specific type, we define it inside that type, alongside the normal methods and variables we might have. Just all about this one keyword static. Essentially, every time you create a custom type, you can internally split it. We have the portion that has no static keyword, that is the normal type as you've learned it so far. And then there's a second portion, a second segment in our custom type with the static keyword, which means this is now a special segment that's creating definitions for the type in general, not for a specific instance of that type. And to access it, we always just use the type and the dot operator, which in this case doesn't mean, hey, go to our table and look for a variable called type, and then use the dot to resolve the context, call the method, jump to the location or whatever. Because value is a type, the computer knows the dot operator means go to this weird third space that we as programmers usually don't have access to, and look up value in there, because it is in here, and call the method. See, one purpose of this third memory space that we don't access, because we don't need to, even though we do it all the time, kind of, indirectly, is it holds all these definitions. All of this code, all of the definitions, this whole thing is cataloged in this third space, alongside a lot of other things. When you call a method, it is basically read from this part. When we call a normal method on value, if we were to make this non-static, if this was a normal method in value, we would execute this in this context, but on the heap, we just store the values. We don't store the program code. The program code is in here, in this third part. When we call the method, we start in this context, but we execute the code from here. If we add a static, it just means we skip loading data from here or from here, wherever we are. We just execute the code directly in here. We don't care about any context from the outside. We simplify things. With a constant value, we don't bother looking it up in our table because the compiler has taken care of it. We just use the value we assigned, and it just looks like we created the variable in our table. We didn't. It's const. With a static, that means we just execute the code that's directly in this third space. We don't care about any context in here or here or here. Just execute the code. Whereas for normal methods, we check out the code, but then we also load the context to provide additional data. And now things get really weird. I'm creating a static variable. It's not just an int coms, it's a static int coms. Static cannot apply to just methods. You can apply it to variables as well. Or fields, as we would call them. And just like static methods are independent from any context in here, on the heap or the stack, so our static fields, static variables, are not tied to a specific context, but general apply to just to the value. There's technically a small table in here, in this third space, independent from where we are. In this third space, now we'll store one instance of this table for the entire type value. This is the same table that will be kept throughout the entire runtime of your program. It exists once for value. Each type can have its own table, but it exists only once. And I can, just like I did with the method here, go through the name value.coms and set a value. Or can read it, as if this was a variable for a normal instance like A and B. But just like with this method, I don't care about specific context. I don't need a variable from my stack to reference anything. I just need the type, the class. So I go to this third space where all the definitions are stored, where the code is, and where all my static variables are stored. and I set the value in here. And no matter how many times I create a new value, no matter how many iterations of that exists, I have only this one static. This one comms. That's a single value that exists once throughout your entire program for the entire category of custom type value. Which does have some interesting implications. What we can do, for example, I'm going to cram it a bit here. We can say comms, which I can access directly. Keep in mind, static int comms is a static variable in here where we execute our code. Normal field val is stored in these tables for specific instances. Each instance of value has its own part in the heap where we store val. Comms exists only once for the entire value, for the entire type value. So if we use a static method, we can actually... I said it again. Why do I say actually all the time? It just knows it. Do I do that every time? Is it happening in every stream? It drives me mad now. God. When we call this method, it might not have the context for a specific instance, because it's not designed to have that, unless we provide specific values, of course. But it definitely knows comms, because it's a static value. There is no specific instance to be attached to, there is only one comms. There's no ambiguity between, do I mean val from here, from there, from there? It's comms. There is only one comms. So I can just use it directly. And I could just do ++ to increment it. And now we have a variable that tracks how many times we've compared two values. Whenever I make a value.r equal, internally it will increment this comms. And I can just read that out. Value, the class name, .comms. Can read that and use that data. For example, for another if value comes greater than 10, blah, 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 we can do things. We could also change the rules. Earlier we had the integer and a boolean. And sometimes we might want to compare only the integer values, and sometimes we wanted to compare the integer and the boolean. We could actually make that... I did it again. We could make that a general definition. We could just say val... I'm not gonna create that field now, but could say value dot compare bool equals false. Right? Compare bool. And then our methods, we could make an if that reacts to this one boolean that exists once, and based on that change the behavior for our entire class everywhere. Now, one last thing regarding these statics. This code as it is right now can be changed to this. And there's no issue with it. I do still require now an instance. I don't get the option to make value.r equal. I would need to actually make... Why? a.r equal or b.r equal or something else. And it will call this as a normal method, which means we do have access to a val, technically. But this method doesn't care about its own context, it cares only about the two values it's provided, and the static field, comms, which it does have access to. These static things are always visible to every single one. all of these instances have access to this one table. They can all see this one static variable comps. And they can all access any static method as well. I could actually... One day I will stop using that word. I could use static to mark this method as a static method and still call it through a.requal, because it is still a value. It's an instance of type value, and because of that it has access to the method requal, which is part of value. It's just bad form to do so. You should, if it's static, use the actual type name. And in most IDEs, the compiler will actually... In most IDEs, the compiler will notify you of this. It will give you a hint that maybe you want to switch to the name. But the end result is all instance-based iterations of your type will have access to all these static data, all these static methods, all these static fields. But if you're inside a static context, if this is a static method, then you have only access to other static methods and variables, not to anything instance-based. So they can always see the static part, but the static part doesn't see them. It's a one-way street. Unless we provide explicit references to an instance as parameter. Static are a weird concept, but there's a lot of cool stuff you can do with it. And it will be very important in the future. But the main reason I've demonstrated static to you right now is because it's the last ingredient that was missing to make the jump to actual programs. We've reached that point. And we're 10 minutes out from ending the stream. Because I'm just gonna tease it, and I'm gonna show you a fully functional program. And next time we're gonna start with that in an actual programming environment. Of course, I first have to get the system to work again. Why is it breaking down now? Let's try that again. That looks better. Okay. Whenever we wrote programs so far, I just added some brackets and wrote some program code. Closed those brackets. And then added some methods next to it and some classes and whatnot. I've kept some things from you, which you already knew. I mentioned that a few times, I think. This code that we're executing right now could be anywhere in our program. This could be part of a method that itself is part of a method somewhere. No problem. My question to you: what is the very first code that would execute it when our program starts? I can have a method that calls another method that calls another method. But what is the very first method that's executed? Is there a first method, or is there some special code that triggers this whole calling methods? Is there normal code somewhere? Quote unquote normal. The answer to that is no. It's always a method. But there's somewhere the very first method that our program runs. Which is kind of an issue if you think about having a program with dozens, hundreds, thousands of different methods. Because which method starts it all? The methods that we start can call other methods. So once we have one method, it will take care of everything else. It will trigger a chain reaction. But we have to decide which method to start with. Because the computer needs to know where we want to start our program. What are the first lines of code the computer should execute? Or just the very first line of code. Where do we start? When we compile our program, the resulting code actually includes instructions for the computer where it should start. And depending on your environment, depending on the language, different options for compilers and whatnot, you might have the option to decide yourself where you want your program to start. You can just create a program with a specific starting point in mind and give the system the instruction, please start here. But for many programs, for many programming languages, that decision is made already. The compiler expects you to create a very specific method which it will call to start the program. And if you don't provide that method, if you don't create it, the compiler will just not compile. It will complain, you've wrote incorrect code, I can't use this. You're missing the start method, the initial method that triggers everything. So we need a very specific method that sets everything in motion. Why is it not? It's an electronic eraser. Why is it? Okay, whatever. It's kind of chaffing. Ah, okay. The where is showing. So let's think about this for a moment. We need a method that will start everything else. So when we call this method, we don't have anything yet. We have nothing on the stack, we have nothing on the heap, we just start running this method. And the compiler requires us to provide this method. What criteria can we expect for this method, given those circumstances? Well, we need a return type, we need a name, and we need parameters. Let's not worry about the return type, because, I mean, if it's a starting method and nobody is there to really call it, then nobody cares about the return type, right? So let's just assume that's void. Let's start there. Then the name. That seems kind of arbitrary. And it is. It's whoever designed the language or the compiler that decides on that name. So I'm just giving that to you. It's called main in C#. The main method is the initial method, the entry method. That's where your program starts. And then the parameters. Well, if nobody's calling the method, if it's the very first code you run, then we don't need any method parameters, right? This is fine. And with that, we have a working method that we can call. Except this is another issue. When we call this method, where do we call it? It's a method. Well, we don't have any variables we can call it on. I don't have an a.main. I've never created a variable a. I have nothing. Stack and heap are empty. But that's only the stack and heap. This third memory space that we just discussed exists, because that's your program. That's all the definitions, all your templates and whatnot. And that means it also has all the static stuff. So we have nothing on the stack or the heap that we could call main on, but if we're to store this in the static portion of our program, somewhere in this third memory space, then we could call the method without having anything on the stack or heap. So this is actually a static void main. Let's space this out a bit more. Static void main. Let's leave the body empty. There's nothing we want to do. This is just an entry method. This is not the signature, but one of the possible signatures for the very first method that a C# program will run. That the computer will call to start everything to get your program going. And it's one of the different methods because I simplified things. Since no one is calling us, we don't need to return any values. So it's void. But if we think outside of our program, there is someone calling us. The computer itself is calling our program. And we can return values to the computer. So this doesn't need to be void. And because the computer is calling us specifically, the computer can also provide values to us. So this doesn't need to be empty. This can actually have parameters. But those are iterations we will talk about in the future, because we're lacking some knowledge for now. There's still something missing in this. We have a method, a static method. And we know static methods are methods we have in this third space that belong to a specific type, to a different custom type depending on, well, where we defined it. Which type does the main method belong to? It's a static void main, but to which custom type do we assign this? Where do we find it? And this is actually up to us. Unlike with the main method, there is no predetermined, you need to have this to make it work. We only need this method itself. The computer does everything else. As long as we have this main method, we're fine. Because there's only one allowed main method in your computer program. If we write a second one, the compiler will complain that we have two main methods, and that's not allowed. So as long as we create one main method, everything else is automatically determined by the compiler. It will know that's a main method, so wherever we put it, that's where we start. So we can just create class. Let's move this down a bit. Class something. Popular choice would be class program, for example. But the name isn't important. It's just, we have a class called something, and in this class we find the static void main. We find the main method, the one main method. And that is where our program starts. I can't write that bracket. Good enough. And all our code goes in here. Or at least the code that will call other code. From in here we can call other methods. Create new instances of different custom types and call stuff on them. And they can create new elements in the stack or the heap and call methods on them and branch out from there. It all starts in here. And so our code before, if you look at this should actually be code in the main method. Because it's our entry point into the entire program. Of course, you might assume we have already a main method that's calling code, and this is just one small segment of our entire program, in which case this could be anywhere really. There's some weirdness though with this model, because it meant we had class value within the class something. And other structs, we had them within another class. And that's not a mistake. That is perfectly doable. That's perfectly fine. You can have classes and structs within other classes and structs, the definitions at least. You can actually it again. You can define a struct within a struct within a struct within a struct. You can just not store them inside one another. Well, no, you can do that too. You can store itself. You can create loops that way, but not too common, but absolutely doable. And still everything works the same as before. It's just there's a bit more we need to discuss when we talk about this. But that way you know that it's possible and there's something coming in the future. And before we leave, one last thing. You need to learn this as well, because we're here already. Classes don't necessarily stand on their own. I mean, we can have one class, we can have another class, or a struct, all next to one another. You can put them in one another, we can put them next to one another, but they all are grouped together in another larger thing. Though you're not necessarily aware of it. You can hide it. But there's another thing that exists that binds several custom types together. And that is, in terms of programming, not really relevant. It doesn't have any effect that changes how we program the code. It is purely a formality. It's a grouping. We group several custom types together, and this group receives a name. And this entire thing is a name. Okay, can't write that far left. Namespace. This creates a namespace, and that means everything we define in here shares a common name, is part of the same group of stuff that has a name. And within that namespace, we can have somewhere a class that does something, which internally has one method, static void main. Or another iteration of the main method. And the compiler will ensure that there's only one main method in one class somewhere in a namespace somewhere inside your entire program. And when we actually, when we finally compile the program and try to run it on our PC, or whatever else we use in terms of devices, we start executing this method. The computer will make the very first method call to main. And once it did, that's when we as programmers take over and our logic now determines which other methods get called and what does our program do. Okay, I've thrown some concepts at you in last minute, but I just want to get rid of them in my mental space, because starting from next stream, we will do actual programming. I give up. In a real environment for coding where you can finally start programming yourself. And you can finally get rid of my bad handwriting, trying to decipher all of this. Alright, with that we're done. For real this time. Have a lovely Sunday, and I'll see you next time.